Cameras, hopefully you have seen it in class as well. A camera is normally represented as two specific matrices. And it's weird to think about, maybe like not intuitive in the beginning, to think about cameras as matrices. But you actually, if you give it some thought, you can imagine like that a camera, or the abstraction of a camera, is essentially the same idea of moving the objects around. So if you think from the perspective of the camera, moving the camera is the same of moving all the objects together, right? So for example, if you pan the camera right, you can think of it as you're moving all the objects to the left by the same amount. So if you're panning left, you are moving all the objects to the right. So that's how computer graphics model cameras. You apply transformations to the objects to give this illusion of cameras. And the whole theory behind this, it's kind of complicated. So of course, James is going to talk about that in class. And there's also, we should definitely read the book to understand these matrices better. But you're going to have to create these matrices here and send them to the shader, and then use these matrices to transform our vertices. Okay, that's the kind of the overall idea. So let's see how to start this. I'm going to start by making a camera. Actually, not making a camera, sorry, making this first matrix called the view matrix. So here I'm going to actually first say that to create a camera, we have to create two matrices. View matrix and projection matrix. The view matrix essentially is used for movement. For example, moving forward, backwards, spanning the camera, rotating the camera around. The second matrix is used for giving the idea of perspective. Right? Imagine if you wanna have perspective in our world. For example, like the objects that are further away, they should look smaller than the ones that are closer to me, like similar to our human eyes, right? That's how we see things. So if you want to actually implement perspective, you have to create this projection matrix. Well, you're going to have to understand this in theory, but thankfully in practice, we already have functions that make this matrices for us. And they are in the library that we gave to you. So let me create a matrix here, call it view matrix. This is a matrix 4. And we have this special function here called set lookAt. And I'm going to take a look at this function here in the library. Here. So it takes a lot of arguments, right? It's actually 9. So it takes 9 arguments. And the book talks about them in detail, but I'm going to give you some like brief description. The first 3 ones define the position of the eye point, or where the camera is. So this is the kind of a global, or the world position of the camera. The center X, Y, and Z, so center is where the camera is looking at. So for example, imagine if the camera is at position 0, 0, -1, and the center is 0, 0, 0, the camera will be looking at, will be positioned in the same, you'll be positioned by 1 unit on the z-axis looking towards the center of the world. So this is like where the camera is pointing at this point. And this is the up vector of the camera. So you can think of a camera as you're kind of using this kind of high right hand rule, where your thumb is the up vector, your index finger is the center vector, is where you're pointing at, and the center of your hand is your eye position, or the kind of the joint, the joint point between these two vectors is the eye position. Hopefully that makes sense. But again, the book has some visualizations, and again on the slides you're going to have stuff like that as well. But that's how you define, how do you create a view matrix, okay? So let me start by making these vectors. I'm going to do let I here be a vector 3. I'm going to say center. This is also normally called at, okay? I'm going to put a comment here. This can also be called a center. And the up. So we're gonna count, like you're gonna set these values here by hand first to see how they change the view matrix. But essentially, I'm gonna have to give these values here one by one. Unfortunately, I have to do them one by one. 0, 1, 2, and then at. Third one is up. So this is how you set the view matrix, sorry. And here we're gonna give some initial values. Let's say we start at position 0, 0, minus 1, okay? And let's say we are looking at the center of the world. And let's say our up vector is 0, 0, 1. These are very standard values to start with, okay? That's, I'm picking them because they are very standard ways of starting this. And I actually remember that the argument should be given as one array, like this. So let's see if this runs. I'm not sending the matrix to the shader, so nothing's gonna happen, but at least let's see if I don't, oh yeah, I have something. 2, 2, 1. I think I messed up something. Oh yeah. Here. Okay. Done. So you're saying, I think you can type it like this too. With the 3 point. No, like this. I don't think so. Yeah, I don't think so. If you saw something in the assignment, like if you saw this notation here, wow, that's pretty cool. I don't know. If there is a shortcut, yeah, definitely go ahead and use it because this is too long. I'm gonna keep it simple right now because yeah, I'm not sure exactly what you're talking about. So I'm gonna keep it this way. But if you feel free to like make it shorter, it's definitely better. Okay, it still works. So it works. It's running. But now let's send this matrix to the shader. Okay, so matrices. This is, you can see this as a transformation matrix. So we can make another uniform here, right? Another matrix. Call this a view matrix. And we're going to simply multiply here on the left everything by this view matrix. Okay. Remember, we are combining these transformations here in one matrix, and it's allowed. That's another trick. That's why, for example, again, having matrix 4x4 matrices is very cool for doing 3D transformations, because we can always do these multiplications. Cool. Should be working, except that we have to send something to this variable. Otherwise, it's only if it's a 0 matrix. So let's send that data. I'm gonna do the uniform as a global variable up top here, just to be consistent. I'm gonna say u view matrix, okay? View matrix equals to null. And then I'm gonna retrieve this uniform together with the other ones. Retrieve view matrix uniform. And this is uv matrix gl.get uniform location. Let's copy this easier. gl.program view matrix. Okay. Done. Now we set the matrix with gl.uniform matrix for fv. We give the view matrix, we give the uniform first. Second one is false, I think it's just transpose. Third one is the view matrix elements. Now you're sending the view matrix to the shader. I'm gonna just compare this with the previous one. Yeah, see? That's it. Huh, honestly, okay, let's run this, see what happens. Problem. We don't see anything. And let me print. Let me print this, just make sure. Not a number. Oh, there's some mirror. Wait, did I mess up? What is elements? Did I get elements? What is the issue? Let me see. Let me print this, guys. Zero 1. Okay, this is good. Let me just see here. Let's see. Second. Let me see where. Let's try to use. That's funny. Oh, I think, yeah, that's, oh wait. Maybe there's something weird, but the up vector should be 0, 1, 0, first of all, because it's the y-axis. Let's see if this is, oh, that was the problem. Okay. I think there was a division by 0 happening somewhere. Yeah, I think, let's see, let's look at the matrix now, should be fine. Okay, the matrix is fine now. Okay, yeah, the problem was just that this was not the right up vector. So we got a problem, but that was it. Okay, this is done. So, but nothing changes, right? It's because I picked the numbers here to be kind of okay. They already like I knew these numbers would give us the same result. Essentially, the camera is exactly at the same location that it was always at the same as always. It was always at this position, and with this setup. But now this turns out to be the identity. If you, or in other words, if you use the setup, you're gonna get an identity matrix or something very similar to it. Let's look at the print. -1. It's not the identity, but it's the negative. Let's see. Yeah, so it's not the identity, but it didn't change anything. What we can start doing here is kind of changing some stuff and see what happens. So I want to play with these values a little bit. Right, for example, what happened if we moved this further back to -5? Now we don't see anything because, so let me, because we are looking, wait, I think we are looking at the wrong side. Yeah, I think we are looking at the wrong side of the texture. 5 and -5. Wait, what? Let me try something 1. So this is, we are looking, -1 is the direction inside, kind of looking inside the screen. So we are looking inside the screen, and we can compare the texture here. It's actually flipped, right? So for example, let's see. This is also flipped. Again, this is because also the way we loaded the texture. If this was not a tile-based texture, it would be easier to see these things. Maybe if it was a smiley face, you'd see how actually the orientation of the texture. But I'm not quite sure if in the first place we loaded this as expected, like as the original image is. Maybe we have to set, when you load the images, there is some parameters to flip the texture here that the book talks about, and maybe you're gonna need to do that in your own texture. But for now, it doesn't really matter. Anyway, let's not get this thing confusing. I'm gonna set this thing here, and maybe change both eye and center here by 1. And essentially, what I did is I moved my center and the at position by the same amount, so I got a pan kind of behavior, right? The same, if I did the same thing with -1, I would move to the other side. Okay, so I move to the other side. And if I want, so with this look at function, I can actually do panning, and I can move my camera. I could even rotate my camera. But these are kind of more complex movements that you're going to have to do with special functions. And this is going to be your job in this assignment, which is how to implement every specific movement of a camera. So, for example, let's see, if I play, I'm not quite sure why we are not seeing, if I change this to be minus, let's say 0.5, I still see same thing. And note that we don't, note that we don't have perspective here. So we haven't done perspective, which means that if I go forward or backwards, I won't see the image like smaller or larger because there's no perspective yet. So I think it's actually, let's add perspective so we can actually observe the behavior of these numbers in a better way. Right now it's going to be kind of tricky to see, to understand these numbers without perspective. So let's make a new matrix here called the projection matrix. And it's going to be set. There's a function again in the library called set perspective, and this is to create a projection matrix. This is create a view matrix. Okay. And let's look at this function in the library. Okay, so this function has 4 attributes: field of view, aspect ratio, near, and far plane. Okay, so the field of view is the angle, kind of, the field of view can be seen as kind of how wide is your view, right? So for example, humans, we don't see 360, right? We see only like maybe 60 degrees. And I know that some mosquitoes and flies, they can actually have a way broader field of view, wider field of view. We have like this narrow field of view that's 60. And the aspect ratio is the aspect ratio of your canvas. The near plane is, I think it's easier to visualize this, but this is the distance between the eye point and this, where do you start considering the perspective. And the far plane is one float number. Again, these are float numbers. This is also a float number. All these 4 arguments are floats. Field of view is an angle, aspect ratio is a ratio, near is a distance, and far is a distance. So near is the distance from the eye point to this plane, is a fictional plane, is where we start actually considering the perspective. And the far is like where you stop considering perspective. So these values kind of define a frustum. So let's make some of them here. Let's set some values here first, and then we can change them. I think the easiest way to understand this is by playing with these numbers. So I'm going to give 60 as our first field of view. As aspect ratio, I'm going to use this. I'm going to use from the canvas. I'm going to divide width by height. Okay. So this is a nice, flexible way of, a general way of solving this problem, because we're going to read from the canvas the width and height, which is like the width and height here. Third one is the near plane, the distance to the near plane. I'm going to put this a very small number. I'm going to put this 0.1, and the far distance, I'm going to put this a very large number, like 1,000 or something. Okay. We're going to have to do the same thing. I'm going to send this to the shader. So I'm going to make here a uniform projection matrix. I'm going to retrieve this uniform. gl.get uniform location, gl program, u projection matrix. Okay. Now we go to the shader. We make a uniform matrix 4. We multiply again this second matrix. Now we have this very This is going to be the final version of our vertex shader calculation. This is how most of the applications use a vertex shader. Most of applications in graphics, they have this structure of a model view times the projection matrix. This allows us to make cameras, to move objects around. So this lets us move and transform objects around, scale, translate, and mirror, reflect these things. And these two matrices allow us to implement camera. So with that, we can send this matrix. I'm going to copy this line and can send the projection matrix elements to the shader. And now with this, we should have perspective. Let's see what happens. If I load this, oh, I got an error, G, line 218. Oh, here for some reason, GL. Okay, see, now it looks like we are zoomed in, right? So let's start playing with these values here now. Let's put 1 here. Now let's put 1.5. See, now you're actually now moving back. So before, without perspective, is hard to visualize, but now it makes sense, right? Now if you move away, we see the cube smaller and smaller. If I start going inside the cube, let's put minus 0.5. If I decrease this number, I'm going to keep going inside the cube till a point that this image is going to, maybe let's do 0.01. Until I don't see it anymore. Because I'm now on the other side of the cube. This is a square, right? This is not a cube. This is a square. So it's a plane. This is a plane. So I believe that there's two things to worry about. Maybe I'm not seeing it because I passed it, or because this value is too, now it's actually greater than the shorter distance. So let's see what happens if I put here 0.01. Let's see if I still see the thing. No, I don't see it. Now let's see what happens if I put -1 here. So the center is now behind me. Yeah, I still don't see it. So I think these are just two small numbers. We don't have to worry much about them. But let's look back at -1. Let's keep this. Let's do some other changes here. Actually, let's go to -2. So you're kind of a little bit, oh no, more. I'm gonna go more, -5. And I'm gonna start playing with the act. So right now you're looking at the center of the world, but what happens if I change this a little bit, right? So now I'm gonna move I'm gonna look, let's see this. Now I'm looking to the left a little bit, okay? So if I put -1 here, I'm gonna look to the right a little bit. I can also look up a little bit if I put 1 here. See? I can also change the Z component, right? And this is now moving what this is doing is, imagine there is a point here that was initially 0, 0, 0. Now I'm moving this point, and then the Z is just like now bringing it a little bit in front of me. So this is 3D, right? So this is a position in the world. So this is the position in the world that I'm looking at. So 0, 0, 0 is the center of the universe, which is also the center, the cube, where the cube is at this point. The cube is also at 0, 0, 0. But I can always select where I'm looking at. So this is, by changing the Z here, I'm gonna bring this point closer to me. Until a point that is gonna, so that's why I'm kind of aligning with the cube. But again, remember these points are independent from the cube. I put a cube there so you can see something, but these points are world coordinates that are completely independent from the cube. So you can put it wherever you want here. So this is where you're looking at in the world. Okay, and this is where you are. And this is your up vector to orient your camera. I'm not gonna play with this up vector for now, but we're gonna definitely have to change it. Imagine if you wanna rotate the camera around itself. When you rotate the camera up and down, the up vector changes. Right? If you essentially when I do this, my up vector now should be changed as well. I'm not changing it here, but it should be changed. If I want to move forward, imagine now if I want to move forward towards the angle that the camera is looking at. If I want to move forward towards the angle that camera is looking at right now, I would have to fix my up vector. Because if my up vector is still 0, 1, 0, I'm going to always only move my camera on the ZX plane. If I do this, I only move in the Y plane, XZ plane, sorry, which is kind of a ground. But if I want to move towards the sky, for example, I would have to change my up vector. And you're gonna, just me saying that doesn't mean much. You're gonna see the challenge when you're gonna hope to understand when you start implementing this thing. But essentially, you're gonna have to play with these vectors to implement your camera. We are almost finishing up. I know these numbers, they are not very clear in the beginning, but the whole approach makes sense. I hope the whole approach makes sense. Do you have any questions about it? No? Okay, so yeah, so you're saying that you should have this before. Well, for the previous assignment, we wanted to kind of just allow rotations without actually, so as a way to introduce this idea of camera as a transformation. So because like when you talk about cameras, it's a whole new topic, and we didn't want to introduce that. We have to introduce it on its own as its own assignment. And hopefully you understood that using a matrix allows you to kind of make these global rotations that now you're making actually a whole camera out of it. And anyway, so there is one last thing I want to talk about, which is how to encapsulate this whole all these ideas, these two matrices in a class. Most rendering engines would have a class called camera. So I think you should do the same. You should create a file called camera.js and make a class called camera. Okay. And maybe here we give, no, let's start like this. So I want to literally bring these guys there. I want to just simply copy for now. Okay. But I want to make these variables part of the class. And okay, maybe here we want something like, maybe here we want some function. Let's fix this first. let's create this, and then when you construct the camera, it sends this variables, this, and then this is global, so it's fine. This is also this. Canvas should be global, so this should be fine. This is also global, so this is fine. And this is projection matrix. And this should be projection matrix as well. I'm gonna actually put this here to keep things organized. This should be this projection matrix. This should be this view matrix. And let's see what happens. Now we have all of this in one camera class. Okay, so you just instantiate that camera, and you have the full capabilities or the same features we just implemented. Let's see. I just have to load this guy. I'm gonna load this geometry, maybe camera, the bottom here. This is not this. Yeah, I'm gonna actually load this first. See, boom, no. What did I do wrong? Camera. Yeah. No, I'm not saying. Yeah, I'm not sure these values are defined at this point. No, they should be, right? They should be. Oh, actually, I'm gonna move. Now that these things are here, I'm gonna move this uniforms updates inside our draw call. Okay, so here, I wanna, similar to here, I'm gonna update the view matrix here. And this is gonna be camera, no, this is gonna be camera.projection matrix. No, view matrix, sorry. And I'm gonna do the same for projection matrix. I'm gonna keep this in the draw function to make sure we use the right, before drawing, we have the right elements in there. This should be done mainly like when you move the camera. I think it's better. It's more like it will be better to call these things when you move the camera, for example, with the keyboard. I think it's better because you avoid calling these things when you don't need. But for now, it's fine. View matrix, projection matrix elements. I'm gonna keep it here before the draw function, and then we don't need this. Yeah, and this looks much better now. That's 5. Okay, let's go back there and make sure this should be U. This is projection matrix, U projection matrix, camera projection matrix, camera view matrix. And this should be, let's see. Camera is not defined. Yeah, camera has to be global as well. Okay. Oh, our canvas, this is one problem. Our canvas is not global, so I'm gonna make this global. So what probably we won't see anything before because canvas wasn't defined in that context, inside the class. So I'm gonna make this global to make sure things are fine. I'm going to also make the camera global so we can access it in the draw function. We can access it here. Let's see. Cannot read property elements of undefined. Maybe view matrix. Projection matrix. And line 119 says not. Let me print the camera here. Let's see what you get. Camera. Oh, it's nothing. There's nothing inside. What is the problem? This constructor class. Wait, did I? There's a problem. Camera. Let me see. Let me print this outside. Let me print this here. It's empty. It doesn't have anything. Constructor, this. And this works. What is the issue? Did I forgot to? Let me print here. This. See what we get. Yeah, we get. Oh, is this entry here? Constructor. Oh, constructor. Is this right? No, I think it was wrong. Yeah, I think it was wrong. It was just a typo. Should be fine now. Okay, there we go. We got it. Sorry. Yeah, too many changes at once. But yeah, essentially it would be ideal to have, it's much better to have this concept of camera that you can easily manipulate. And then you have your calls in here that access the camera. Yeah, and this makes your life much easier. Why? Because, and why is that? Because you can make functions here now. For example, to move forward, right? Or maybe move backwards. Right, maybe pan left and then pan right. And then you could simply call whenever you click, for example, whenever you press and the user press W, you call move forward. And then moving forward requires you to compute, for example, compute the forward vector. So where I'm looking at now, in the beginning, it's 0, 0, -1. Sorry, this should be, maybe like, let's keep this like this. Wait, -1, yeah, like this. Sorry, let's keep it like, this is what I meant. Let's keep it like this. So I'm looking at the square. But if I want to move forward, my forward vector is is 0 is always I minus at.
Okay, I
Sorry.
found this on
Or sorry, at minus I, actually, sorry. It's always at minus I. F equals at minus I. So we have to compute this, because imagine if I was looking a little bit to the left, if I pan my camera, my forward vector is not the z-axis anymore. It's some other vector. So you need to always compute the vectors, and you're gonna have to think about how to implement these camera movements. And we're gonna give some information here. If you look down in your assignment, there is some information down here. For example, if you implement the move forward function, I might say this one. It's I minus x. Sorry, this is I minus x. When I look at, this is my forward vector. So here I have the steps. I have the steps to implement move forward, and then implement move backwards. We're gonna keep adding more information for pan left and pan right. But basically, when you finish that, you'll be able to do something like this, right? Camera dot move forward here, and then it's going to move your camera forward by, let's say, you can even pass here maybe like how much you want, like 1, 2, 3. We haven't specified that, but maybe you can give here like a speed or a distance that you want to move by, and then you move that much. And then if you press A, you pan the camera. Press D, and so on and so forth.